Okay, so welcome to the lecture 49 in this course Classical Mechanics 1. So, in this course we have learned Lagrangian formulation, Hamiltonian formulation in details, and then we have learned Poisson brackets, canonical transformation last week. Last few lectures we have spent on canonical transformation, and today we are going to start a new topic, which is two-body central force problem. So, we are going to discuss the classical mechanics of this two-body central force problem. So, first thing, that why and what is what. So, why is central force? Why is central force problem? And second thing, or rather what should be the first one, that what is central force. So, what is central force and why we are going to study this. So, I'll answering these two questions, will give you the motivation why we are going to study central force problem. Okay, central force problem means that the potential for this force is only depends on the magnitude of the position vector. So, if the potential depends on the magnitude of the position vector, that means it does not depend on any angular dependence, no angular dependence. So, such system later we will see they will have a symmetry, rotational symmetry in the. So, we will see the such system or central force problem will have rotational symmetry. Okay. So, but why we want to study such system? Because this is simply because in many places in physics we see the central force, role of central force. For example, the planetary motion or the motion of electron around the atom is kind of central force problem. So, central force problem is important in that sense. Starting from the planetary motion, the motion of earth around the sun can be described by, because there also the force is proportional to 1 over r square, and similar to the case of electron motion around the atom. Okay. So, in first we will study that if you have a two-body problem, then how we can reduce it to the in two bodies potential, and that can be reduced to the one body problem. So, first we will try to learn, because two body means now you have a two particle two body problem. Two body problem means you have 6 degrees of freedom in 3-dimensional in usual 3D space. So, you have to now, instead of handling 3 coordinates or 3 degrees of freedom, you have to handle with 6 coordinates, 6 degrees of freedom. So, doubly difficult. So, first we will see that two body central force problem can be reduced to effective one body problem. So, first in this topic we will learn that it is possible a two body central force problem to to an effective one body problem. So, this theory we will learn, and then we will proceed after that. So, first today we will learn that two body central force, two body problem, how it can be reduced to one body problem. So, let us start with the Lagrangian. So, if we have a Lagrangian, it is two bodies, so it will be R dot, similarly R2 dot will be the Lagrangian. So, first particle is say with mass m1, so R1 dot square plus kinetic energy. The kinetic energy for the second particle will be m2 R2 dot square, and then say potential energy which depends on R1 and R2 in general. So, it is in general. Now, if the potential is central force, so for the central force, this potential should depend on the magnitude of this position vector, relative position vector. So, it will be function of mod R2 minus R1. Okay. So, let us see then in this situation, and let us denote this R2 minus R1 as R, position vector R. So, this is, let us denote, this is equation 1, this is equation 2. So, if I draw a axis, okay, and say this is my first particle and its position vector is R1, and say this is my second particle. So, this is M1, this is M2, and its position vector is R2. Okay. So, now let us go to the center of mass of these two particles. Okay, center of mass, and let us denote that this is the position vector of the center of mass. So, let us denote M1 plus M2 as M, and R is the position vector of center of mass. So, center of mass is somewhere located at here. So, center of mass. Okay. And now, let us see that can we write this Lagrangian in terms of in the center of mass frame, or in terms of center of mass coordinate and the relative coordinates. So, M is to in 1 in terms of center of mass coordinate, R, and relative coordinate R. Okay. So, by definition center of mass, we can write that M1 plus M2, that also denoted by capital M, is M1 R1 plus M2 R2, or maybe R equal to M1 by M R1 plus M2 by capital M R2. So, let us this equation as 3. So, this equation 3. Okay. And 2. So, if we express R1 and R2 using 1 and 2, so let us use equation 2 in 3 to express R1 and R2. Okay. So, how we will do that? We will just substitute. So, let us do it for you. R equal to M1 M R1 and R2 I will substitute in terms of M2 M, R2 will be R plus R1. Okay. So, that means R1 M1 plus M2 by M R1 plus M2 capital M of R. Similarly, okay, so better to write in terms of R1. So, R1 is the position vector of the center of mass, means M2 by capital M R. So, let us denote this as equation 4. Good. And then similar fashion, if you make R2, calculate R2, it will be R plus M1 by M R. So, this is equation 5. So, let us equation 5. And let us substitute back in the Lagrangian. So, what was our Lagrangian? Lagrangian was half M1 R1 dot square plus half M2 R2 dot square, okay, minus U R1 minus R2 minus R1 mod. Okay. Okay. So, if I substitute this, I will get half M1 R1 dot square. So, R vector dot minus M2 by M R dot vector square plus half M2 R2 I will get R plus M1 by M capital M R dot square minus U function of R, small r. Okay. Relative small r is the relative separation between the two particle, and which is here, this is your R. Okay. Okay. So, now we will simplify this little bit. So, let us collect R dot square. So, R dot square, if we collect half M1 R dot square plus half M2. So, M1 plus M2 R vector dot square. Okay. Then let us collect the R dot square, okay, small r dot square. So, it will be so R dot square. So, it will be M1 half is outside, M1 M2 square plus M coming from the first term, second term M1 square M2 by M by half square, okay, and the cross term. So, cross term will be minus M1 M2 by M R dot, from second term R dot capital R dot, and the from second term it will be plus M2 M1 R dot R by M. Okay. So, you can see this cancellation of this term with this term, and you have the potential term as it is, potential term minus U r. Okay. So, what we remain the Lagrangian now? Lagrangian half m r dot square plus here you will see there should be correction m square. So, it should be, if you take m1 m2 common, so m1 half is automatically there, m2 common by m square and then m1 plus m2, okay, r dot square minus ur. Okay. So, this further can be simplified, m r dot square plus half m1 m2 by m r square minus ur. Okay. So, now what happened? You can see that the center of mass coordinate and the relative coordinate are separated. Center of the potential does not depend on center of mass coordinate r. So, rather you can see that the center of motion, center of mass has a free motion. It is a free particle, motion like a free particle, because it has only kinetic energy half m r dot square. And so, now among the 6 degrees of freedom, 3 degrees of freedom associate with the center of mass, and that has a free motion. So, things are very simplified. We have 3 of the degrees of freedom, that means center of mass is moving freely in a direction, straight line. So, it is not very interesting. So, rather we should go to a center of mass frame and in the center of mass frame this r equal to 0, because now we will have only 3 degrees of freedom. So, only 3 degrees of freedom remaining related to relative coordinates. Okay. That means, if we look at the center of mass, so let us write the Lagrangian in the center of mass frame. Lagrangian will be half m1 m2 by m r dot square plus minus u r. So, you have a single particle, this is a single particle Lagrangian. With the relative coordinate r. Okay. So, what is the mass of this single particle? So, this term half m1 m2 by m is, we can denote with mu, and this is nothing but reduced mass. The system, as 1 over mu is 1 over m1 plus 1 over m2. Okay. So, physically what is happening? Physically, that we had 2 particle system. So, let me draw the axis again. So, this is my first particle m1 and this is my second particle m2, and somewhere between we have center of mass, this is M2, so this is R1, this is R2, this is R, so this is center of mass. So from the center of mass, if we look at the system, we will see that the system behaves like a one particle system, one particle motion in the potential UR, but that particle has mass which is the reduced mass. The mass will be the reduced mass of the system. Okay, that we have seen mu and denoted by mu. So from the center of mass, we have effective, in the center of mass frame, the two body problem effectively reduce to a one body problem. With reduced mass mu. So from center of mass frame, the two body system is now described by the Lagrangian half mu r dot square plus minus u r. So moving in the, so this is the effective one body system, and now we will see that this is remarkable, and this is possible only because of central force problem, because potential does not depend on the it depends only on the separation, relative separation between the two particles, and does not depend on the center of mass coordinate. Okay. So this is the so we have learned that the two body central force problem has been reduced to effectively to one body central force problem, one body problem. So now we have a system of 6 degrees of freedom to 3 degrees of freedom, because now it is effective one body problem. So 3 degrees. Whereas the other 3 degrees of freedom, other 3 degrees of freedom are associated with the center of mass, which in this case moving freely in the because the potential does not involve the center of mass coordinate. Now let us study this system. So to study this system, further, we know the central force problem, the particle under central force happens in the plane. So a plane, two-dimensional plane will be good enough to describe a central force problem. So central force problem, so motion under central force happens on a plane. So let us characterize this system in terms of polar coordinate in a plane. So if we write x equal to r cos theta and y equal to r sin theta, kind of this polar coordinate. So a plane can be described by this r from going to 0 to infinity and theta 0 to pi. You can have describe a plane, xy plane. So we have from xy plane can be written in terms of r theta. Okay. So what will happen that in terms of r theta, this Lagrangian, by making this substitution, you can change it to half mu r dot square plus r square theta dot square minus u r. So, this will be the Lagrangian for the effective one body problem. Okay. Now, few things are immediately we can find by looking at this Lagrangian. First of all, we can see that the coordinate theta is cyclic. If this coordinate theta is cyclic, that means there will be some conserved quantities. Some conserved quantities. So, let us see what is this conserved quantities quantity. So, theta is cyclic. So, momentum conjugate to theta will be conserved. Okay. So, what is that momentum conjugate? P theta will be del L del theta dot by definition. So, it will be half mu r square to theta dot. So, mu r square theta dot. So, what is this quantity? We will see this quantity is nothing but the angular momentum of the system. At the very beginning, I said that central force is basically rotational invariant system, and we will see the angular momentum, because angular momentum of the reduced mass. So, mu r square theta dot is nothing but the angular momentum of the reduced mass, or the particle reduced mass particle. So, two body central force problem, we just thinking of a one body with reduced mass system, and that reduced mass system's angular momentum is conserved. So, we get a new insight that in a central force problem, angular momentum is conserved. That we obtain by reducing it a single body problem and writing the Lagrangian in the plane, and we will find that it is conserved. So, in the next class, we will proceed with this Lagrangian, and we will see the aerial velocity. In the next class, we will see the aerial velocity will be conserved in a central force problem independent of the specific form of the potential. So, potential, it depends only on r, but what will be its form, that does not matter. Independent of that, your angular momentum of the system will be conserved, and the particle swept out equal area in equal time. That is the properties of Kepler's planetary motion, that aerial velocity will be constant. So, that independent of the potential, will see if the particle moves in a central force, its aerial velocity will always be conserved. Okay. So, with this, maybe we will stop here today. So, in the next class, we will proceed from here and we will find the equation of motion, how to find the orbits and what will be the trajectories, etc. So, in next class we will concentrate on this. So, maybe I will stop here, and in the next class we will proceed from here by considering the equation of motion and what will be the trajectories, how we can predict the trajectory without solving this problem exactly, and so on. Okay. Bye for now.